The algorithms are watching. They are learning. They are shaping our world, from what news you see to who gets a loan, even to the very future of jobs and global power shifts. We live in an era of unprecedented data, where every click, every transaction, every sensor reading fuels a hidden engine. But how do we truly understand this engine? How do we make sense of the tidal wave of information that dictates our collective destiny? The answer lies in statistics. Not the dry, dusty numbers you might recall from school, but a vibrant, critical framework for navigating the chaos of modern information. Statistics is the science of collecting, analyzing, interpreting, presenting, and organizing data. It's the lens through which we can discern patterns in market volatility, predict the spread of an emerging virus, or even uncover biases within the AI systems we're deploying at a dizzying pace. Think about the latest inflation reports or unemployment figures dominating headlines. When a government agency releases the average price increase for consumer goods, or the percentage of people looking for work, they are using descriptive statistics. This branch focuses on summarizing and organizing data in a meaningful way. It's about presenting the facts of what happened, allowing us to see a clear snapshot of economic reality, like saying a nation's GDP grew by 2% last quarter. But what about predicting the next economic downturn, or forecasting the success of a new AI model? That's where inferential statistics takes center stage. This is the art and science of drawing conclusions and making predictions about a larger group based on a smaller sample of data. When pollsters predict election outcomes based on surveying a few thousand people, or when medical researchers determine a vaccine's efficacy from clinical trials, they are using inferential statistics to extrapolate from the known to the unknown, attempting to glimpse the future. Understanding this distinction is not just academic, it's crucial for interpreting the daily deluge of news. Are we being shown a definitive snapshot of a situation, or an educated guess about what's to come, based on limited information? In a world grappling with information overload and deepfakes, knowing the difference empowers you to evaluate claims and predictions with a critical eye, whether it's about the future of work or geopolitical stability. To dive deeper, we need a common vocabulary. Imagine you want to understand the political leanings of an entire country. The population would be every single eligible voter in that country. However, surveying millions of people is often impractical or impossible. So we select a sample, a smaller, manageable subgroup of voters that ideally represents the larger population. From this sample, we calculate a statistic. For example, if 55% of your surveyed sample intends to vote for a particular candidate, 55% is your sample statistic. When we try to estimate the true voting preference of the entire country's population, that true, often unknowable value is called a parameter. Our goal with inferential statistics is to use the sample statistic to make informed guesses about the population parameter. Now, let's talk about the raw material of statistics, data itself. Data comes in different forms, and recognizing these forms is fundamental. We generally categorize data as either qualitative or quantitative. Qualitative data describes qualities or characteristics that cannot be measured numerically. Think about the brand of smartphone someone uses, or their preferred social media platform. It's descriptive, often categorical. Quantitative data, on the other hand, consists of numerical values that can be measured or counted. This includes things like the number of AI servers a company deploys, the processing speed of a new chip, or the daily fluctuations in a stock market index. Quantitative data can be further divided into discrete data, which can only take specific, distinct values, and continuous data, which can take any value within a given range. Beyond this, we have different levels of measurement that dictate what kind of statistical analysis we can perform. The simplest is nominal data. This is purely categorical, with no inherent order. Examples include the operating system on your computer or your nationality. We can count them, but we can't rank them. Next is ordinal data. This also deals with categories, but there's a meaningful order or ranking. Think about a customer satisfaction survey where you rate service as excellent, good, fair, poor. We know excellent is better than good, but we can't quantify the between them. Is the gap between excellent and good the same as between good and fair? Not necessarily. Then we have interval data. Here, the data has a meaningful order, and the differences between values are consistent and measurable. Temperature in Celsius or Fahrenheit is a classic example. The difference between 20 and 30 degrees is the same as between 30 and 40 degrees. However, interval data lacks a true 0 point, meaning 0 doesn't represent the complete absence of the measured quantity. 0 degrees Celsius doesn't mean no temperature. Finally, ratio data has all the properties of interval data but possess a true 0 point. This includes things like income, height, weight, or the number of downloads for a trending app. 0 downloads means no downloads at all. From the rise of AI to shifts in global economies, these fundamental concepts are the blueprint for understanding our increasingly data-driven world. Mastering this vocabulary, from descriptive to inferential, from population to parameter, and across all data types, is not just about crunching numbers. It's about developing the critical mindset needed to navigate the hidden patterns, surprising consequences, and future impacts of the forces shaping our present and our future.